Okay, so let's do the periodic function. So suppose f of t plus capital T is f of t for some capital T positive. So think of sine, right? Sine of t plus 2 pi is sine of t. So capital T is 2 pi. Okay, so let's find its Laplace transform. So this is in your book as well. E minus s t. Okay, so we have to capitalize on the period that the function is periodic. So we split into the periods. Okay, that's step one. Let me write it in summation form. Okay, now let's use change of variables to centralize the integral. Okay. Okay. Good. Let's bring out the exponential and use periodicity. Okay, so we brought out the exponential term. And that's it. Now we use geometric series. The geometric series formula. And that's it. So this is the Laplace transform of any periodic function. Okay. So I took the example from the book and modified it. So let's do that. Okay, so solve the IVP. So this is an RL circuit whose voltage is periodic. So it switches between -1 and 1. Let me draw a picture. So 1 up to time 1, more space. -1, up to time 2, again 1, up to time 3, and then -1 up to time 4, and so on. Okay. Let me call this star. So, as usual, take Laplace transform of star, and so that will give you yt is Laplace inverse of Ls plus r, L of our signal plus y0, which is 0. Good. So yeah, I have to find the periodic signal. I have to find its Laplace transform. Period is 2, as you can see from the picture. Okay, so how do you do this? You split the integral. So 0 to 1, you know that the function is 1, and then 1 to 2, you know your signal is -1. Okay, so I did the computations, and you get 1 plus e to the minus s, and 1 minus e to the minus s. So that's the Laplace transform of the periodic signal. Right, so back to our problem. Let me write it all together. So Ls plus R times S divided by 1 plus e to the minus s. Okay, so what do we do now? So I will do this a bit clearer than in the book. We use geometric series. Minus r to the k is equal to 1 plus r. So this is, we put it aside, and we call this r. And so we get -1 minus e to the minus s k. Use linearity. To get this. Good, so now we have to find this. All right. By partial fraction, we have the following. Okay, and now I will use a linearity. So I have sk over s. That's one of the terms. Okay, so let me find them one by one. So this is the sk times the Laplace of 1, and then use the translation term. So 1 times step function minus k. Let me do another term. So we have sk s plus r over l. This is sk l of the exponential. I guess I should say what translation theorem I'm using. Let me write it on the side as a reminder. So in general, where is it? Here. The Laplace transform of the exponential mirror like this. Right. So you have this function. If you take its Laplace inverse, it's equal to the shifted function times the step function. Okay, so this is our equivalence. So let me keep it on your screen. So you will have e to the minus r over l t minus k times the step function. Okay, that's it. So here a is k if you follow the notation. All right, so let me write you the final answer. So there's two more terms, but they're handled the same. So we have an infinite sum, and yeah, minus 1 to the k, 1 minus step function, and there's a shifted guy. So okay, you might be wondering, does this have infinitely many terms? The answer is no, because of how should I say it? So recall that ut minus a is equal to the step function t bigger than a. So it forces it forces k to go up to t for one guy and k t minus 1 for the other. So let me write it here. Because you might be wondering if it was finite. Okay, I think that's it. for now. Okay, so this is if you remove the step function, and these are finite because t is finite. Okay, thank you.